So this is our second or third lecture in Chapter 9 dealing with gas power systems. We've covered the internal combustion engine, the Otto cycle, the diesel cycle. Today we move into basically the Brayton cycle. This is a cycle modeling gas turbines that produce mechanical power. Basically run a power plant, maybe to generate electricity, burn natural gas to generate electricity, but you don't have to only use natural gas in a gas turbine. You can use actually liquid-based fuels. If anybody served in the United States Navy, and a lot of their surface fleets are run by gas turbines. Anybody taking a cruise out of Galveston, one of those? Guess what the power plant is in most of those modern cruise vessels? Gas turbines, gas turbines. So what they'll do is drive a shaft for the propulsion system, as well as probably a system for electricity generation on board. All right, so this is a image of the gas turbine. I'm going to blow it up on the next slide and spend a few seconds talking about it. So it's a bunch of highly engineered device. It's complicated. I just give you an overview of it. Here's a shaft coming out right here. That's where you would bolt up something to it. You would bolt up an electric generator. Okay, on this shaft right there. Okay, what is this? This is all for air to come in. Typically air comes in from above. A big air filter, big system above the gas turbine. And then the air comes down in some ductwork, and it would rotate around and then turn 90 degrees and then go into this section, which is the compressor. And the compressor is a sequence of stages of stators and rotors rotating, stationary blades, stators and rotors, and it reduces the cross-sectional area because it's being compressed. It doesn't need that much area, and so then it comes out. And what we're doing in the compressor is boosting the pressure. So the pressure at the end of the compressor, let's say state 2, is much greater than the pressure at the inlet to the compressor. Right after the compressor, you have some sort of combustion system. I know the illustration's not that good, but these are some cans, like combustion cans, and there's a ring of them coming around and around. I don't know, maybe 12, 14, 16, I don't know. You have to do the count. This is a cutaway. And you can see this image of some combustion happening in the cutaway of this can. So now I know that the air will do a little, turning and mixing into the can. Then you have that combustion. Some of it may bypass the can and then mix with it right afterward. Little tricks to make sure that this thing is running and the flame doesn't go out, and handling the many variations. But now you have high temperature gases. The pressure does not change in the combustion system. The pressure is relatively constant. If anything, it drops a little bit. Okay, then you need to expand it through turbines. And the turbines are sequence of stages of rotors, stators and rotors, just like the compressor, but you're extracting mechanical energy out of the fluid. And what you're going to do is going to be expanding that cross-sectional area. Now, they often are busted into two sections for the turbine. One section of the turbine needs to extract enough work to run the compressor. And it'll come back on a shaft to run the compressor. So that's because the compressor is going to take a lot of mechanical power. And then maybe a second set, or maybe there's a gearing system, depending on the design. Okay, a second set of expansion would be connected to this shaft that is to develop power and provide it external to the gas turbine. That's a second set of turbine blades to expand it. So there you get the mechanical power. Now, this is for power production. You do not want high enthalpy on the exit. You do not want high kinetic energy on the exit of the exhaust gases, but you have a system to slow them down. Hopefully they come out, little diffuser section at the pressure. You have to kind of push them through some exhaust system, but just think about getting it to atmospheric pressure. Okay. So you get it out. Now, when we talk about the gas jet engine, they strap underneath the wing of an aircraft, not this lecture, next lecture, or maybe the following lecture, we'll have a compressor, combustor, turbines, but we will only extract as much energy out to drive the compressor. And the rest of that energy you convert in a nozzle so it goes out as high kinetic energy as possible, as high a velocity as possible out the back of that jet engine. Hence, you get a large thrust. And it's going to push the aircraft down the runway and up into the air, into the sky. The principle of thrust. But here, for power plants, it's low kinetic energy, low exit enthalpy. We want to put as much energy into the shaft. Okay, hopefully that was helpful. So we want to model this. It's so complex, we're just going to break it into simple components. First component, compressor. What do we take in? Out air, ambient air. We then put it into a burner or combustor, different names, and then you expand it through the turbine, and then you exhaust it to the system. So you would have compressor, burner, turbine, just like we showed in the real system. And yes, you do have some fuel coming into the system. Hence, this air, mostly nitrogen, but oxygen in it too, is still a lot of nitrogen, but now you have carbon dioxide and water vapor. It has the products of combustion that expand through the turbine. Okay, so these are exhausted. That's close to what we have. Okay, in the real system, you'd put some states. Okay, talk about state 1, state 2, state 3, state 4. And what we're going to do is we're going to idealize this cycle. Just like we had the real internal combustion engine, then we said, okay, we're going to have this approximation called the Otto cycle. Well, we're going to do the same thing. We're going to have the approximation called the Brayton cycle. So the Brayton cycle needs to complete the loop. And there's a number of other assumptions in it. We're not going to have gases changing, and there's going to be carbon dioxide and water vapor as a result of combustion. We're just going to have pure air always. So what you do is you say, I'm going to have a compressor. The combustor is going to be modeled as a heat exchanger, expand through a turbine, and then we're just going to take it and complete the cycle, put it through a loop, so that we have another heat exchanger which models the intake and exhaust processes by replacing it with a heat transfer to the surroundings. So the convention is to put state 1, but you don't have to, it's a cycle, but state 1 is the inlet to the compressor. Then state 2, the exit to the compressor, which is the inlet to the combustor or heat exchanger or burner. And then state 3, it's out of the combustor, out of the heat exchanger, and into the turbine. And then state 4 is out of the turbine back into a heat exchanger to complete the loop. So we're going to do an ideal air standard Brayton cycle analysis. So I think we understand the components. The 4 components, 2 of them are just heat exchangers. 1 is a compressor, 1 is a turbine. And we're going to do an air standard analysis of it. And an ideal meaning, we're going to first, everything's internally reversible. It's the best that you can get. No friction. Okay. All right, so it's always air, no combustion products. A lot like the air standard analysis associated with auto and diesel, the same list. Oh, it's always going to behave as an ideal gas. The combustion is too complex. Just model it as heat addition, Q in. The exhaust and intake are too complex. Just model it as Q out, or a negative. I'm going to switch it and model it both this way. So this would be a heat rejection. And if you show it as positive into that heat exchanger, that'll be a negative quantity. Okay. If they throw the additional and they say, oh, it's a cold air standard Brayton cycle analysis that you need to do, additional assumption that it's around 25 degrees C or 298 Kelvin. I know that's a perfect conversion, but when you look at the table, it's right at 300 Kelvin. Get the constant specific heats on that line of 300 Kelvin in our tables. If you want to interpolate, you can, but it's not going to improve your answer. Decay for air, 1.4. All right. We're reminded of these simple equations for an ideal gas, assuming constant specific heats, undergoing isentropic processes. This is out of the chapter 6. We used both of these in the Otto and the diesel cycle. And I said, put this one on hold. We'll pick it up and use it heavily when we get to the Brayton cycle, and that's what we are. We're getting to the Brayton cycle now. Okay. So this one is in terms of the pressure change across the compressor. All right. So here's a problem. You might as well start solving problems, right? It says air standard Brayton cycle operates with this inlet pressure and inlet temperature to the compressor. The compressor pressure ratio is 9. That throws students for a loop. I need to talk about that some more. So, but let's finish reading the problem and then we'll come back. The maximum temperature in the cycle is 1600 Kelvin. On the basis of a cold air standard analysis using this value of C sub E and that value of C sub P, and oh, by the way, if you take the ratio, K comes out to be 1.4 for those. Determine, hey, the easy one, thermal efficiency, and the next easy one, back work ratio. You solve one or two of these problems, you know there's a lot of steps to answer those two simple questions. So, what would be the steps that I recommended when we did vapor power cycles, when we did the Otto cycle analysis, diesel cycle? It's the same type of steps that we want to go through. What do you think step 1 involves? Make a schematic, that's right. And what are our components? And then label the states between the components. So, let's go ahead and do it. Let's go ahead and put a component here. Let's put it compressor, burner. This would be a turbine. And this would be, I don't have a better name for it, I just call it a heat exchanger. The flow goes, state 1 is the inlet to the compressor. State 2 is the outlet to the compressor, and then inlet to the burner. State 3, and then state 4. So those are our components, and those are our states. So we should know what's going on in each component. And we should know something about property changes. Now, the next one is we want to start to sketch our TS diagram. And maybe you could also do a PV or a pH diagram, but I'm just going to emphasize the temperature entropy diagram. There's other useful property diagrams, but let's just stick with the TS. Okay. Well, when you model this cycle on a temperature entropy diagram, you're really processing the second law for each of those components, as well as the first law. So let's do this. What would be a standard assumption about the heat transfer in the compressor? 0. It's not a heat transfer device. It's a work, device. How about for the work in or out of the burner? 0. The burner's a heat transfer device. It's not to do work. How about for the turbine? Its standard assumption is it's adiabatic, and then the same with the heat exchanger. Those are big observations, and I'm glad that most of you, it looks like, are following along. All right, so maybe when we come in here and we draw this dashed line, what is the professor doing? And they put a little CV, control volume analysis for that compressor. You know what? We're shifting. When you did Otto and diesel cycle, it was a closed system analysis of a trapped amount of air in a piston cylinder undergoing processes. This is open, not closed. And we have inlet to the flowing across the boundary of the control volume and outlet flowing across the boundary control volume. It's all steady state, and we're going to neglect changes in kinetic and potential energy. So you can write, let's do the first law for the compressor. And I'm going to do this. I know that the work is positive into the compressor, but I'm going to show it work out of the control volume. That's our sign convention. And then this W for the compressor is going to be a negative work. All right. So what is my equation? Steady state, no heat transfer. Maybe I should have written it like this, that the W for the compressor, the work per unit kilogram, kilojoules per kilogram, boils down to change in H, a change in the property enthalpy, right? And because I've shown it here, it'll be the H1 minus the H2. Yeah, that'll give me a negative answer. Did you have a comment or question? Oh, you were going to answer my question. Thank you. Okay, good. Now let's go over here and do the work of the turbine. That's probably the easy one. The harder one was the compressor. Oops, what that line do? The work of the turbine. Okay, so that would be WTURB if you like long subscripts, or WT, whatever. Isn't that H3 minus H4? You're getting very good at the first law for an open system, control volume. Okay. If you need to go slower, go slower. How about this one? We're going to show Q in to the burner, B-U-R-N. All right. Do the first law. It's going to be related to a change in the enthalpy. It'll be H3 minus H2, right? And here again, it's a little convoluted, but I'm going to show a positive in for Q on this heat exchanger, but I know I'm going to calculate a negative Q into that heat exchanger because it's really heat rejection. And it'll be the H1 minus the H4, first law analysis. Okay, you do a second law analysis for each of the components. Maybe we write it out for the compressor. Maybe it's been a while. So for the compressor, you're going to have 0 is equal to the mass flow rate of S out at 2 minus S1 is in, plus any Q coming in divided by some TB. But guess what? Why is that equal to 0 for the compressor? No heat transfer, no entropy transfer with the heat coming in. And the last term is this the sigma dot. So if there are any irreversibilities, then it would show up. But since it's internally reversible for an ideal Brayton cycle, then what do we conclude? S2 is equal to S1. Now, when you go and compare S3 and S2, they are not equal. S3 is higher because there's heat transfer coming in, and that's increasing the entropy. Not because there's sigma dot, it's just because there's heat transfer coming in the burner. So if you wanted to, you just say S3 is greater than S2. All right, how about now compare S3 and S4? They're equal. And then here, I know that the S1 is lower than S4 because there's heat out. Okay. So now I could probably do a pretty good job of this temperature entropy diagram. Maybe I tuck it in down here just for space purposes. Temperature entropy. When you do a temperature entropy diagram for a Brayton cycle, I encourage you to put 2 lines of constant pressure on it. Why? Because there's really only 2 pressures. The high pressure, the burner pressure, and the low pressure, that heat exchanger pressure. Okay, so we put 2 lines of constant pressure. This would be maybe the high pressure, and this is the low pressure. State 1 is at the low pressure. and it's going to be relatively low temperature. We put it through that compressor to get it up to high pressure, state 2, and you do it reversibly. We just talked about S1 is equal to S2. It's isentropic compression. Boom, there you go, there it is. Now you're heating it, so the temperature is going to go up, 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 until you get up here to state temperature 3. Often there's a cutoff. Material or other considerations, they'll say that we have to limit that maximum temperature. The performance of the system would be better if we have better characteristics of materials that allow us to have higher temperatures, but there's still temperature limits on materials and seals and everything else in the component. Okay, so it's T3 is often given as a limit to the system. That's the exit after the burner. Then we come in and we expand it through the turbine to 4, and then we cool it back down. And there's your cycle. Maybe you add some notation. This is some Q into the cycle. Maybe this is adiabatic. Maybe this is some heat rejection, Q out of the cycle. You could annotate it to help understand what's going on. So those are the first 2 steps. There's a lot involved in it, isn't there? Now the other steps are pretty easy. Get a table and get the key properties of all the states. So for this one, I'm going to say there's how many states? 1, 2, 3, and 4. All right. How many properties are of interest? Pressure in units of kilopascal, temperature in Kelvin. You could put another column. If you had to count for variable specific heat, you would add an H column because you'd be in table A22. But because this one is a constant specific heat, a cold air standard analysis, I know I don't need that. I just need the temperatures. Because when I come up here, let me flush that out. What is H1 minus H2? Is it C sub P, T1 minus T2? Yeah, that's what it is. All right, how about up there? Is this H3 minus H2, is that C sub P when you make that additional assumption that constant specific heats, it's C sub P times T3 minus T2? Yeah, that's right. And then down here, it's C sub P T3 minus T4, true? And then this would be C sub P T1 minus T4. Did I help work that through? Okay, let me hit one of the key points that I'll get questions on all the time. And because I post my stuff on YouTube and I don't block comments, you know, I'll get all kinds of comments. A lot of them, thank you, appreciate it. Some, you're wrong, professor, you don't know what you're talking about. And this is one I'll commonly get right here and right now. All right. What does the P on the C, what does that subscript P on the C, the specific heat, mean? Constant pressure, right? All right. And then you learned about C subscript V, constant volume. All right. They look at the process for this heat exchanger going from state 4 to state 1. Is that a constant pressure process through the heat exchanger 4 to 1? No problem there. Okay. Let's take a look. Going 1 to 2 through the compressor. Is that a constant pressure process? No. This, whatever adjective you'd like to throw in there, in San Antonio, Texas, putting this stuff on YouTube, doesn't know what he's talking about. I've gotten that, you know, stuff. Whatever, but they don't care about that. They just always, there's some, I know, there's you've seen them, there's some that just like to find fault. You know, anyway. So, is it wrong to write C sub P delta T for the compressor when the compressor is obviously not constant pressure? You see that it is conceptually a little challenging. I never said thermodynamics was easy. Sometimes it can be a little like, this doesn't make sense. But you go back to what an ideal gas means. Maybe it's back here, or right back here. What are these three things? Why did I write three things when I said, oh, it behaves as an ideal gas? Most people would say, hey, PV is equal to RT all the time and stop there. But they shouldn't stop there, should they? They should also say the internal energy is not a function of two independent intensive properties, but only one. And that only one is temperature. And you tell me the temperature, and I will tell you the internal energy of the ideal. I don't need to know the pressure and temperature, just the temperature. This is a big deal. U is only a function of temperature. Likewise, H is only a function of temperature. True? Okay. So you go back, you say, what is the definition of C sub B? What is the definition of C sub P? That works for a solid, that works for a two-phase liquid vapor mixture, that works in the supercritical region, works in the ideal gas region. Just what is the definition of this property? And you go back and say it's something like the rate of change of U with respect to T holding V constant. All right, C sub P, the rate of change of H with respect to T holding P constant. Perfect. But now somebody says, I want to use this very general equation for only an ideal gas. H, this is the key observation, is only a function of T. So mathematically, do I need to use this type of derivative? Or can I replace it by this type of derivative? I can replace it with the ordinary derivative. I don't need to do the partial derivative. So for an ideal gas, this becomes the ordinary derivative of the enthalpy with respect to temperature. Right? And that's a bad-looking H. Here it is. Is it restricted to pressure constant only? Nope, you just lost that restriction. And now somebody says, I would like you to calculate the H2 minus H1. You say, no sweat. I see this equation right here. What I'm going to do is I'm going to take that equation and go dH is equal to C sub P dt. Mathematically, is that okay? And then you know what you're going to do next. You're all experts in calculus. You integrate. You integrate from the lower limit to the upper limit, consistent limits, and so you get that H2 minus H1. So you're 1 to 2, 1 to 2 is equal to, and if you have constant specific heats, that comes outside the integral, you have C sub P T2 minus T1. If it's not constant specific heats, other people have done the integral for you and put it in table A22 for the H's. Easy. All right, well, where did I get derailed on that one? I forgot. But I need to jump back here and finish this out. We have 8 values in this table that you need to get. 8 of them. See that? And guess what? 4 of them, or a few of them, are given in the problem statement. Just read the problem statement again. It says 90 kilopascal. Where does that go? Yeah, this is 90 right there, isn't it? All right. Where does the 300 Kelvin go? Right there. Okay. And the last is the 1600 Kelvin, which is the maximum temperature. State 3, exactly. 1600 Kelvin. So those were the easy ones. Now we have to do a little bit of work, but the pressure is easiest. You can probably get all of those 3 remaining pressures with just a little observation here and there. So, how about the pressure at 4 compared to the pressure at 1? Same. So, I color code that blue. You had to use a little logic. You had to know, hey, the pressure between 1 and 4 is the same. Then you look at this information, the pressure ratio is 9. What are they giving me? Now, a lot of students will not read this word correctly. And they'll think, okay, 9. They're giving me V2 divided by V1 is equal to 9. Is that what they give me? No. They gave me P2 divided by P1 is 9. All right. I am tired of grading final exams with errors and mistakes. Right here is a spot where I'll find a lot of students will make an error or mistake. Believe it. Believe me. Have I emphasized that already? It's like, okay, I'll write this problem straight out of the book, right out of the stuff I've solved in class, just like this. And I'll say, oh, now it's 11 for the compressor pressure ratio. And a few students will immediately put something like this down. They'll think it's a volume change that's being specified. It's a pressure ratio that's specified. So anyway, can you figure out what is the pressure at state 2 and pressure at state 3? 9 times 90, 810, and 810. Very good. Now, now we have to figure out this temperature at state 2. How am I going to calculate the temperature at state 2? And let me do this. I'm going to pause the mic, walk around, and I'm going to get 5 people to show me on their calculator or on their piece of paper what is the temperature at state 2. You have to calculate it. Okay? You're going to use that favorite isentropic ideal gas equation. That's what equation you're going to use. All right, so we're using the equation that T2 divided by T1 is equal to P2 divided by P1 to the power K minus 1 divided by K, right? And so the T2 is equal to 300 Kelvin, that's T1, to the pressure ratio 9, to the 1.4 minus 1, so 0.4 divided by 1.4, that exponent. Little bit of work to get that exponent, right? And when you do that, this comes in at 562 with some other digits on it, but let's drop it right there. 562, right? All right, how about to go from 1600 to get T4? It's going to be a very similar equation. It'll be the 1600, then you'll have the 1/9 of the K minus 1 over K, because it's isentropic from 3 to 4, but you're not increasing the pressure, you're decreasing it. And that pressure ratio is 1/9. And so it's 0.4 divided by 1.4, and this then, this is T4. So T4 comes in at 854. Agree? Thank you. All right. So now the last part, or one of the last, is I need to get a table of the energy transfers for each component. So how many components? 4 components. And I need the Q's and the W's. I need to get some space, so let me do this. I'm going to erase right in here so I can fit it in. I'm just going to erase right there as well. And so for each component, there's 4 of them. One is the compressor. One is the burner, one is the turbine, and one is that heat exchanger. I'm interested in the Q and the W, and it's kilojoules per kilogram. So for every kilogram that goes through that device, what is the heat transfer in kilojoules, as well as for every kilogram that goes through that device, what is the work transfer in kilojoules? We've done this a lot. And we worked on quite a few of these, but there's 8 of them that we have to get. 4 of them, 4 of the 8, half of them are zeros, aren't they? So I'm going to pause. I want you to populate which ones are zeros. 2 of the Q's and 2 of the W's are 0 in this table. And then I want you to take and use these temperatures over here and start getting the non-zero values calculated. Okay? All right, I was glad to see a lot of people have finished this problem out already. So it was 0, 0, 0, 0 for those. And then people were making the calculation. So it's C sub P delta T. That's what you're doing again and again through this. And so we came in with negative 263.3 on the compressor work. And it's a negative because I'm going to sum that column, and I want it to work out that way. And then it's 749.7, and over here in the burner, 1043.2, and negative 556.8. When we do the net Q, we add that column. It's 486.3, and then for the work column, it's 486.3. They match. I'm happy. At least I know it doesn't appear to have an error. I still could have an error, but I know I definitely would have an error if they didn't match. Okay. And then some people said, let's get that thermal efficiency. And when they calculated the thermal efficiency of the cycle, it came in at 46.6%. And then the backwork ratio, BWR, came in at 35.1%. Again, the thermal efficiency would be the net work divided by the Q in to the boiler, or the burner, not the boiler, burner. All right, or combustor. And the backwork ratio is you have the ratio of what the turbine, the fraction that has to go back to feed the compressor that's out of the turbine. So it's 263.3 divided by 749.7 to get the 35.1%. Very good. You ready to move on? Pretty impressed. A lot of you were doing this pretty good, pretty quick. So let's say we solve another problem, but this time the same inlet parameters and everything else, but they say the compressor isentropic efficiency's 83%. They don't have 100% isentropic efficiency. You're shaking your head because you know this means a lot of work. But this is a lot of work, and the turbine isentropic efficiency is 91%. So it would be the same approach. The one thing that you want to do, though, I think if you can get the temperature entropy diagram and get it correctly, you'll be able to solve this problem. So do this. When you're studying the Brayton cycle, there's two lines you want to put on. Lines of constant pressure. They're isobars. This is the low pressure, and this is maybe the high pressure. Okay. We're going to start state 1 coming in to the compressor there. So far, if it was ideal, if it was 100% isentropic compressor efficiency, then it would have gone straight up, and we would call that state 2S. Now, when you're given this isentropic efficiency of the compressor is still able to achieve the same pressure ratio. That's the assumption. So the pressure ratio didn't degrade. You're still going to get up to that top line. State 2 actual has to be on that top line, that constant pressure line, the high pressure line. So this is a question I ask. Should it go over to the right, or should it go over to the left? I put dashed because of irreversibilities, the lower than 100% isentropic efficiency. To the right. Why? Why is it over to the right and not over to the left? Because when you do a second law analysis, the entropy going out has to be higher. S2 is no longer equal to S1. S2 has to be higher, sweeping away the entropy that was generated because of irreversibilities. You go back to the compressor and you'll find S2 is equal to S1 plus sigma dot divided by m dot. When sigma dot was 0, S2 is equal to S1. Can sigma dot ever be negative? Violation of the second law. Sigma dot has to be positive when you have irreversibilities. Hence, S2 has to be greater than S1. All right. We then bring it out of the combustor at state 3. And we used to put it through a perfect turbine down to state 4. But now our turbine is still going to expand the same pressure ratio, so it's going to end up on that bottom line. State 4 is going to be on that bottom line, but it'll either be to the right or to the left. And I know that if I ask this question and I get an honest answer from everybody in the room, it won't be as high a percent correct as the other one. Most of you, I would say 90-some% got the first one correct. Hey, yeah. The 2 actual is over to the right of 2 isentropic. So, which one is it going to be? Is 4 actual to the right or is 4 actual to the left? I'm going to pause, walk around, and collect a few answers. All right, I think given a little bit of time, everybody figures it out that 4 actuals over there, and the same entropy calculations that when you have S4 coming out after the turbine, it's the entropy coming in, plus if there's any entropy generation inside the turbine, normalized by the mass flow rate through. So there it is. Got it? If you get that illustration in your mind, then the rest of this is easy. Okay? In the interest of time, I'm going to move on, but you need to be able to quantitatively complete a problem like this. But in the interest of time, I'm going to move on. And this is what it looks like, drawn to scale. I had to normalize the entropy calculations, but other than that, temperatures to scale, and from this point, the entropy calculations are right for that. So it kicks out from state 1 to 2 actual. 3 is limited by the temperature, and then this is 4 actual. Look good? Okay. Here's a question. The compressor, this is what we're focusing on. It's not 100% isentropic efficiency. It was 90% isentropic efficiency, but then it degraded and it changed to 80%. How does the exit temperature change? So you have the exit temperature, assuming the isentropic efficiency is 80%. And you want to compare that to the exit temperature, assuming that the isentropic efficiency is 90%. And it's either greater, equal, or less. It's choice A, B, or C. I need to let you think about that problem and then answer it. I'll pause, walk around, and collect your answers. In the interest of time, go back to this diagram. You're going up to the same pressure ratio. It used to be it would come out at the lowest temperature if it was 100% isentropic. But if it was 95%, it's a little higher exit temperature. If it's 90%, if it's 85%, if it's 80%, what's happening is the temperature, the exit temperature is coming out higher, 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 right? As the turbine has more irreversibilities. Not the turbine, the compressor has more irreversibilities. So it's A, isn't it? All right, I need to allow you to think through these, but here's another question. Don't call it out. Just write it down. Answer A, B, or C. What about the pressure change? Don't call it out. I only have 6 minutes, don't I? All right. So, okay, let's do this. Let's go back to our favorite temperature entropy diagram. We have a line of constant pressure and a line of constant pressure. And we go from here to there, or here to there, or here to there, or here to there. And this is, degrading the performance as we go that way. But what is that line of constant pressure? This was too easy of a question, wasn't it? But it trips you up, makes you think. It's B. The assumption is we achieve the same pressure ratio. Professor, I think if you have some friction in that compressor, it's probably not going to have the same pressure ratio. Don't overthink it. The assumption in this book and every other thermodynamics book at this level is that the efficiency just makes more work and makes it come out hotter, but achieves the same pressure ratio. Okay? All right. Oh, enthalpy. Talk to me about the exit enthalpy. If it's 80% isentropic efficiency versus the exit enthalpy if it's 90% isentropic efficiency. You have an answer already? All right, so why is it A? Why is it A? Yeah, it's the same idea that enthalpy is a function of temperature, and the enthalpy goes up with temperature. And so we said already that T2 is going to go up if I have lower isentropic efficiency, hence H2 actual goes up. So A is the best. Entropy. Entropy. What about S2? What does that do as the efficiency changes? Good, 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 good. This is a better way to collect responses. I like this. And then just look at that temperature entropy diagram. Now focus on where it's drifting, right? It's going higher and higher, S exit, as the irreversibilities increase and as the isentropic efficiency of that compressor goes down. Well, I have 4 more questions, but I'm not going to be able to ask them. They go with the turbine, don't they? Tell me what the temperature does as the isentropic efficiency goes down. What does the exit temperature at 4 do? Good, 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 good. Yep. Good. Yeah. Pretty nice, huh? I think some of the people in the back have advantage, though. But they actually are some of the earliest answerers. You know, they give the answer first. Protected. No, it's A. Do you want to do the pressure? Right. You're right. You're right. You're right. You're right. You're right. Yep. Yes. Yes. Yep. Yep. Again, that's our assumption. The pressure ratio doesn't change even though it's getting isentropic efficiencies changing. Do the enthalpy and then do the entropy. I thank you for your attention. There are some excellent videos on gas turbines out there. So if you're interested, go look at some videos on gas turbines, how they operate. Thank you for your attention.